Imagine a tiny chip, the thing just blinking a LED when we are first learning the embedded system. Eventually grows up to simulate an entire electric vehicle safety system, speed, battery, collision detection, and all running in the same time. Hey, welcome. I'm Animesh kullu, a BTech student from Jalpaiguri Engineering College, along with my teammate Debjit and Supradip Karmakar. This is our capstone project of emertex embedded system internship, as we called it EV ADAS dashboard. We have STM32 for our brain of the computer or our microcontroller. We do not require any hardware components. Thus, you are using Fixing Lab for simulation purposes and overall coding platform where we can design our microcontroller as STM32 UID and a communication protocol. Coming to next page, our agenda. This layout shows the roadmap of our presentation. This literally show the order in which the firmware itself was built on peripheral and one subsystem at a time. The stage 1 we have the foundation. This covers our tool setups, the basics of ARM and the STM32 architecture where we are going to run our program. And the part 2 we got signal and sensing. Here we have ADC theory, the analog to digital conversion processes, and separate channel for reading the accelerator, brake, battery temperature, and streaming the data over UART. On our third purpose is the most important, where we have EV plus ADAS engine. This is our most important criteria of our project as physics models for speed, state of charges, and regenerative braking, and layered on top collision collision avoidance, blind spot detections, ultrasonic sensor detections, and all are running into it. And finally, we have the telemetry and the dashboard, the UART protocol designed for a command in which we can finally show our output through our dashboard system or our MATLAB system. Coming to next, motivation. The one of the biggest question arises in our day-to-day industry. Then why we are making this EV electric machine, or what is the need or purpose? As the EV is stands for the electric vehicle that is powered by electric motor and battery system. Thus, it's completely without the uses of any kind of external fuel. We can directly generate or run our car on the basis of electricity. Thus, plays an important role in revolutionary industrial ideas as maximum companies such as Tata, Tesla, Mahindra, etc. Even two-wheeler companies like Ola are using the EV system. Thus, it provides an essential purpose. And going through our embedded system program, we also learn how to build one. Now, let's check starting with the development environments and tool. The development environments tool we are using or working on host target setup. The host is our computer or laptop running the STM32 QID that we actually write, configure, and build our code. The target is the PCM lab or Pixin lab, in which the simulation is done with the help of model of blue pill board STM32F103. The microcontroller entered in the software. So one of the fairly question why we use the simulation purpose instead directly running on the hardware platform. The best example is to practical or theoretically enhancing that we our project is running smoothly. After that, we can implement our project in our actual hardware. The entire system dependency, like physics dependency, the address logic, can be live streamed on a dashboard platform with the help of honest testing and demonstration can be done with our development tools or our fixing lab. Coming to next step, we will understand the ARM Cortex M architecture behind the SMT32 F103. Going before further detailed specification, I want to give a sense of scalable data or why ARM architecture matters all over first. Over 95% of our smartphones use ARM Cortex. More than 200% or 200 silicons vendors license our architectures or buildings for our own chip designs. About 30 million ARM chips are shipped globally every day. Thus, the ARM plays a very important role in our circuit. On building, we have the Cortex A, which we generally use for our Android systems and application purposes. We have Cortex R, that's most efficient for real-time observations and real-time uses of the system. And for our project, we are using the Cortex M. The Cortex M3 core plays an important role. It has up to 722 megahertz and altogether a 64 kilobytes of flash memory with 200 kilobytes of SR RAM, which is low cost and essential for our project design and management running for our simulation projects. Coming on next, now we will understand less how the actual power it's working on, starting with a very small thing of our embedded system that's blinking a LED light. Blinking a LED light performs the basic or the first step for learning our embedded system code. In this code, we are going to toggle our LED light, which is present in our pin number 13, with the help of HAL GPIO toggle pin system with a delay of 500 seconds. Thus, it shows the PC13 as active low and active high. This means the onboard LED is wired to ground and it's actually pin drives to low, not high. Toggling it still and it's blinking with about a 500 microseconds delay. Coming on next is the blocking design and real-time limitation in which what pushes us to the next topic as the timer and interrupt. The timer interrupt plays an important role in which the hard delay of the blocking statement is entirely on the CPU while it's performing some operations. The single LED blinking becomes a bottleneck for the network processors, like reading the sensors or running the physics calculation at the same time in the background. In the day 2 of our emertex embedded system course, we learned about how timers and interrupts are worked in our project. Let's walk through with timer and prescaler 1 by 1 multiplied with the prescaler of 7199 and a auto reload register set to 999, in which we are going to calculate our timer or the counter to count up to the performed value of 999, in which our timer clock is running at 72 megahertz, the typical blue pill default statement, and driving with 72 millions by 72 million gives 1 Hz of rate per second for doubling the LED bulb. And coming to the next, now we are coming to our ADC fundamental task. It plays a very important role in our system as it stands for analog to digital converter. The analog is basically a kind of noise for our system. So we need to convert it into our digital part, or in order to process our analog signal, we need a digital conversion. As analog signal, if we plot it in graph, it will show continuous signal fluctuations and happen all the time. Thus, a proper constant DC source or a digital signal of 0 and 1 is required for our purpose or our register for our operations. And thus, we are using 12-bit mapping process of ADC, in which our 3.3 volt is represented as 4095 of our mapping process, and 1.65 volt is represented as 2047. Coming on next, we have our part in which we have holding 4 channels of URT. The URT is connected without potentiometer display, in which the potentiometer plays the important role such as the acceleration paddle, the brake paddle, the battery state of charge, motor temperature, and thus. And it is connected with the channel or pin of PA0, PA1, PA2, PA3. The acceleration is completely dependent on our physics model, which if we want to increase the speed of our system. Similarly, our braking pattern is also dependent with our physics system, how we want to decrease the speed of our system. And finally, the most important part, the battery or SOC of our system. It displays how much battery we have left for our process and how much time it can run. It's completely dependent on the acceleration and the braking system for our system design. Thus, now I want to hand over to my friend Debjit for upcoming representation of the next slide.
Okay, so first of all, I want to thank you, my friend Animesh, for explaining the fundamentals and basic foundation of the project. So now let's submerge ourselves into the main system architecture or the system core. So first of all, our project is named as EV ADAS, Electric Vehicle Advanced Driver Assistance System. What are they? An electric vehicle is a vehicle which runs on electricity or battery operated systems. So to simulate that in our project, we first have to give all the data to the simulator about how it will work because a machine does not understand. We have to make it understand in a way that we have to give some mathematical calculation it will perform and it will give us outputs that will look like the real world scenarios. So first of all, for electric vehicle, we have to calculate different kinds of variables like speed, acceleration, brake, and many more things. And for ADAS part, and ADAS is a system which helps users to give some kind of warnings or advices about how to drive and give an idea about the car surroundings, like a car in like a car in front of us or like a car beside us from either from the left or from the right. So how it will work? For first of all, for the ADAS parts, like such a front area, which is speculation or right or left, we have three ultrasonic sensors, names as HCSR04. And for the data, like for EV, like acceleration, brake, SOC, mean state of the charge or temperature, we don't actually in a car. It's ac- it's the these data variables are generated based on the car conditions. but for our simulation, we don't have that kind of capabilities. So we have to use potentiometers for these variables. Then we have our main brain, or can be said as the heart of the system, is the STM32 blue pill board, which will do the all the necessary calculations and give us the final result. Then we have a communication protocol, UART, or uh, known as asynchronous receiver transmitter or universal asynchronous receiver transmitter, which gives a data rate of capability of 1,15,200 bits per second, and which helps us to communicate between the board and the simulation protocol. And we have a Python dashboard to simulate all the data in a graphical manner. First of all, we have to give some assignments to the pins or blue pill board, or like say for some like PA0 to PA3 for ADC channels, PA8 for timers, some for some for communication protocol UART signals, some for uh, some GPIO pins for ultrasonic sensors, some pins for blind LEDs, some for buzzers. We can see it the table. Now let's move on to the next part, that is the control module. As I already said, we have to divide the project in two parts, EV and ADAS. For the EV part, we have EV control module. What is it? It is a module which performs some mathematical operations to derive some functions which will help to understand the car conditions in the simulation. It says it has data like speed, torque, SOC or state of the charge, range, power, mode, regeneration active, which is a lot to take on from for now. We'll explain that part by part in the next. First, and also it have some constants like max speed, what a car can capable of achieve in a simulation, a torque, what a car motor can have such capability to provide in the for in case of full acceleration or full throttle. Regenerative max means a full capability of a car or motor to generate a backward thrust or torque in case of full brake. Also have different kinds of variable constants like brake threshold, drag coefficients, mass factors, all of that. So let's get into the main mathematical calculations. First of all, the speed model. Generally, look, in the simulation, we can input the acceleration, brake, this kind of variables, but we have to actually calculate the mm, torque, mass factor, torque, on and the speed from that about at what current state is the car in now based on the inputs. So for that, we have to derive the acceleration first. Acceleration is actually derived from a formula which is given in the presentation slide, as you can see. It's divide. It's calculated based on the motor torque. It is currently in now, and the drag or the brakes applied on the motor, and what is the mass of the car. Okay. After that, if we have the acceleration, we have to update it with the current time, which based on that. If let's for example, we have an acceleration at current time at 0. Okay, so at current state or time at 0, then it gives a speed at 0. But as the time increases, we have to update it acceleration based on the acceleration factor to get a proper speed or smooth speed curve of the car. Besides that, we also have a clamped value. What does clamped mean? A clamped value is given to provide a limit of how a car can reach to its top speed and also prevents it to get to the negative speed. the highest value, as we discussed earlier, is 200 kilometers per hour, and the lowest is 0, not less than that and not greater than that. Here we can see the mathematical calculations used in the code, like float speed, float drag, and speed kilometers. The calculations are all done in this way. Okay, so as we get the speed, so in the next part, we have to get the SOC, or state of the charge, because the speed is directly affect the charge, because an EV runs on a battery. Besides the speed and acceleration, we also have to calculate for the charge and how much charge is left, because otherwise if we don't have a calculation, the user cannot understand when will the car will stop, how much charge it left, how long he can drive with the current scenarios or state. Okay, so for that, we also have a calculations about for using this formula, delta SOC. The delta is here used because the state of a charge is continuously changing based on the current power usage. For that, we have the power in with which multiplied with time per total kilowatt hour available. Well, as per, let's assume we have a car which drains and 5 kilowatt at power at standstill condition. Okay, so it helps us to model a real motor in simulation. Uh, and also beside that, we we have given three modes to the our EV. Like in general cars we can see in regular life. They are given named as eco, normal, and sport. As the name suggests, they have three different types of characteristics. In sport mode, the car has the full capability or full power, and this can give the maximum speeds conditions. Normal mode, when a car is driven in an average state and not the highest power and not the lowest power. It gives an user or an average mileage and average range. Okay. After that, we have eco, which is the most power efficient mode of the whole EV car. As we can see in the three modes, how the system will operate and how the system torques, how much range we can get at an approximate calculation. And for that, we have an let's say variable range in the code named, and then that gets given by SOC, the battery watt, the mode it's current, and the kilowatt hour available in the system. Or sorry, the kilowatt hour used per kilometer. Okay, next go on. After the charge is used, yeah, up until now, we have only see how the charge is drained. But due to the efficient working of a car, you also have a way to regenerate the state of the charge. Means when a car is running, it's have to drain its charge, but there's also a way to regenerate some of its charge to increase its range. Besides completely depending on the battery. That is regenerative braking. In regenerative braking is a way in which we can generate a small amount of charge by by braking by braking. Regenerative braking is a motor method that is efficient and helps in our many way. Okay. For that we have seen here the mathematical calculations. What does regenerative braking needs? How does it work? And regenerative braking generate a regenerative torque which will work against the current acceleration and brake. If the regenerative braking exceeds the acceleration pedal, then the car will start to decrease its speed and a charge is starts to generate. But besides that, it also have some uh, disadvantages, like it generates an heat, it gen it generates a huge heat. Okay, on the and give a higher pressure to the motor. So but it helps us to regenerate charge, which increases range. That is our primary EHA. The range and the efficient system is our primary achieving goals, achievable goals. Okay, so the regenerative braking is yes explained here. Like, how does it work? It works in the simulation by reading the brake pedal. Then, based on the brake percentage, it generate if the then we have to check if it is greater than the threshold to get into the regenerative region. Of if that threshold is achieved, then based on the brake pedal, we have to give it a scale of how much regenerative level it's achieved. Based on regenerative level, we have to derive the motor torque, which is a negative in nature. After that, we have derived the how much motor torque negative motor torque is generated, which helps us to recharge the battery. Okay, next go on to the next slide. That is explained. Now we have completed the EV part. The EV part helps us to understand how a electric vehicle work, but that is not our primary target. Our second target is to implement the ADAS engine and ADAS Advanced Driver Assistance System, which helps a driver to drive safely and gives warnings and advisory to how to give an idea about the surroundings of the car. Like we can see here the world view, or it's also given in the simulation. The ADAS use three ultrasonic sensors, one in the front and two on the side, left and right. These three ultrasonic sensors is used in three different. In the front ultrasonic sensor is used for detecting any car in front of the our AV. So to detect any kind of forward collision, and also it calculate a time to collision or how much range is suitable so that a car can avoid. And if a car can came too close to a in front car, then it also gives warning that if how much time we have the driver get to handle the situation. Okay. Beside that, we have two such a side ultrasonic sensors, left and right, which gives user about the idea of blind spots beside the car. A blind spot is a spot where the user can't control or can't able to see, or that can cause accidents. For that, we have left and right ultrasonic sensors, and the blind spot detection only works if the car is above 20 km per hour speed. And based on all the data, it gives different types of warning, like front collision warning, blind spot warning, and time to collision warnings based on the very based on the different different set thresholds. Like front collision warning only works if the front distance or the front car the gap the gap between the front car and our EV is less than 50 centimeter and it goes critical. If it's less than 20 centimeter, blind spots for less than 30 centimeters, and the speed is greater than 20 km per hour, and time to collision warning also if the time to collision between the two cars goes less than 3 seconds, and critical if it goes less than 1.5 seconds. Okay, so next we have to get to the our ADAS features implemented. As I'm already explain all the parts like front collision, time to collision, blind spot detection. Beside that, we also have to add two other features, that is parking assist and overspeed advisory. Parking assist helps. Parking assist use all these three sensors all these three sensors to help a car park the car without having any trouble to the user. Okay, which only works if the car speed is below 10 km per hour, and an overspeed advisory which gives warnings when the car hits the speed above 120 km per hour. Okay, next after that we have fault detections and alarms, four level of alarms. The we have designed the alarm system in a four level of priority. Okay, the first level of priority, the no prior, the none P0, which gives that all the no kind of critical conditions has arrived. The car is working in a completely normal state. Second is the advisory state, which is used for blind spot detection, which gives the user advice that there is a blind spot generated. You should take a look at that. The warning priority that gives the user that there is a chance of any kind of incident or accident. So please take a full attention on that. And critical is a condition in which it gives a complete high cost, highest priority warning that there is no more chances. And in that time, also we have a buzzer which only works in kind of which gives a single beep in kinds of advisory priority and a double beep in kinds of such a warnings priority and a complete rapid beep in case of such a critical priority. Okay. Here is the different types of registers used in the system. Other than that, all the priority of level alarms, we have all the alarms which are used here. The fault OT or over temperature that generates an auto fault when the motor temperature hits above the 90 degrees centigrade, means the motor is overheated. Second, we have the SOC, fault SOC, which gives an warning about the low battery state. The collision warning, generally, the warning that gives us idea about the front collision is about to happen, and also other reserved like sensor timeout or fault com, which can be implemented in the for future uses and also used in the actual devices, actual cars. Okay, so next get to the next part, that is vehicle state machine. For easy coding and better a smart system, we have implemented a machine. Five state machine means a car can be described in the code, for easy understanding is that machine is can be in five states. That is a park state, a ready state, a driving state, a regenerative state, and fall state. Based on the state, there are different kinds of alarms activated and different kinds of protocols executed. Okay, and we have different kind of conditions of entering and exiting the state that gives here in the slide. Next, we have the UR telemetry protocol. It's kind of the mouth of the whole system, which tells the current conditions of the car to the simulator. As we can see, the UR telemetry protocol, we have two lines. One line gives the all the necessary data to run the EV system, like speed, state of the charge, torque, motor temperature, acceleration, brake. All this data is necessary for the EV part. And secondary, we have line 2, which gives the ADAS data like front distance, left distance, right distance, time to collision, what kind of collision, blind spot, alarm, fault, all this kind of data. This all data goes to the our Python dashboard, which use this data to generate the simulations. Beside that, we also have some live parameter injection and the UR, which is normally not used, but in case of if we have to use it, like we don't have to use the Python dashboard, but kind of see what happens when different kinds of values or different kinds of states occur. For that, we have the live parameter injection, like the SOC set about what will be the state of the charge at the current condition, temperature set, what will be the motor temperature, what mode the car is working, what kind of faults, if we inject a fault, what type of what's a behavior the card gives us, the if we cleared the fault, what kind of protocols actives again, the current status, all of that using the live parameter injection. After that, we have to get into the main simulation part. For that, I will like to hand over to my another friend, Supradip Karmakar. From the journey here on, we will be guided by him. So, thank you, and I am very much grateful for for getting on the journey until now.
Thanks, Debjit. You and Animesh covered the fundamentals and the core system architecture in details. From here, I will cover the simulation part, how all this data comes together on our dashboard. A quick recap of our full build journey, the result we validated, a live demo, and finally our key takeaways from this internship. Now let's talk about the final piece, the dashboard. We built this using Python and a library called matplotlib. It updates 10 times every second, so it feels live. There are three main parts. First, the speedometer. Second, the battery panel. And third, the speed history. First, the speedometer, which we see in every EV car to monitor to speed. Second, the battery panel, a bar that shows charge percentage and how much driven range is left, along with the current trip mode. Third, the speed history, a rolling graph showing the last 60 readings. There is also an EV matrix panel showing torque, accelerator, and brake percentage, motor temperature, and any fault codes, and an adult bird's eye view, a top to down picture of the car showing obstacles in front and on the sides, with the color coding of green for normal, orange for warning, and the red for critical. Let's quickly recap the whole project. There we built it in 9 phases. We started with setting up our development tools like STM32 Cube IDE, Lab, and Python. Then we worked in basic hardware, LEDs, buzzers, and timers. After we read sensor like accelerator, brake, and motor temperature using ADC. Next, we build the actual EV logic: speed, torque, battery, and driving mode. Then we added ultrasonic sensor for collision warning and blind spot detection. After that came to the fault and alarm system, which flags problem using priority levels. Finally, we sent all this data, our UART, to a computer, added a command cell to control it live, and built the Python dashboard to visualize everything in real time. This slide shows that we actually tested and confirmed working. The speed and battery reading updates smoothly and behave correctly. Battery drains when driving and recovers when braking. The collision detection reliably spots obstacles closer than 50 centimeters and turns critical when 20 centimeters with a red warning. The blind spot monitor works correctly above 20 km per hour without false alarm. The over temperature fault triggered above 90 degrees Celsius, safely cutting motor power. The Python dashboard displays all five panels live, and we even added a demo mode that works without real hardware. Lastly, we tested the UART cell by manually setting speeds and triggering faults. Everything worked and recovered properly. Now we are switching to a screen recording to show the whole system working live, from Lab simulating our STM32 chip through UART communication straight into the Python dashboard.
Hello, it's Debjit again. Up until now, we have gone through the complete project from either be the fundamentals, either be either it be the project system code architecture, or either be the Python dashboard. Now it's time for the simulation part. So first of all, before going into the simulation, we have to get through the code. Here is the STM32 Cube ID window where we can see we have a main.c file which includes all the header files of other components. Like we have a header file for EV control. Here, the EV control C file, which is connected to the EV control header file. Here, all the necessary EV control setups have been coded, like the EV drive mode changes, how the drive mode will change based on the values, the acceleration, brake, SOC, temperature channels, how it will behave under various conditions. Then we have the ultrasonic header file. Here's the ultrasonic C file. Here is the ultrasonic C file. In the ultrasonic C file, first we have defined the ports, then the front, left, and right variables. Then we have this. Then we have the full mathematical calculations about how the ultrasonic sensors get the distance. Then we have the adders file. Here is the adders.c file. Here, based on the ultrasonic sensors distance data, the adders file will give the alarms or fault detections warnings. Then we have the fault file. Here is the fault file, which only works for the fault calculations and necessary data. It includes ultrasonic files because due to the capture of the distance data. It checks the motor temperature, SOC, collision warnings, flags, all of that to generate the faults necessary. And then we have the UART shell. Here's the UART shell. It includes all the files, and UART shell is primarily used to communicate between the blue pill board and the Python dashboard. Then we have the buzzer file, which only does the three modes: single beep, double beep, and rapid beep based on the fault conditions. And we have first initialized all the necessary variables like EV, ADAS, and fault, the timers, the UART. Then we have uh, main void signal, main code lines like UART initialization, timer initialization, ultrasonic initialization, ADAS, fault, buzzer initialization, and then based on the time, we are where's the time part? I'm sorry. Uh, Here is the EV data line and the ADAS line that's been sent to the through the UART protocol. And then you have the EV update files, the clam files, and the little clock divisions. You Now if we build the code, we will get a debug, that's be a binary file. First of all, we will have to upload it in the local board. So let's load the binary file. As you can see here, first of all, in the spare parts of a, we have four potentiometer setups, three ultrasonic sensor setups, one buzzer, four LED setup, and a virtual terminal setup. The four here is the four potentiometers. The first potentiometer is for the acceleration, second is for the brake, third is for the SOC, and fourth is for the motor temperature. Three ultrasonic sensors named as front, left, and right connected to the respective pins. Front is PB0, PB1, left is PB2, PB3, and right is PB4, PB5. There are four LED setups: PB8, PB9, PB10, PB11. The buzzer is 13. Now let's start the Python part. For starting the Python code, we'll have to first go to the command prompt. I've already loaded the command prompt. For loche root, here is the command to run the Python file. First of all, here is the Python file. The Python file includes the matplotlib library and numpy. Then it shows, then first of all, using the PySerial, it collects all the data that had been sent from the Bluepill board. Then based on that, it does the graphical representation. Okay, so let's start the Python file using these commands. If we want to, we can start the demo using this command Python, the file name, then the demo. And here we are using COM1 and COM2 connections using the VH port pairs that we have used on the software. So let's start the Python file. Here is the Python file. Now, based on the data, we can check how it's changing. Right now, the break and the A both are at 0 state, and it's the mode is in eco mode at the starting. Now, if we uh, increase the acceleration full, the speed starts to increase, and we can see the acceleration is 92%, the motor torque is 983 Newton meters. Once it reaches to the 20 kilometers speed, now if we change the ultrasonic data, like here, here as the let's say front distance goes away, the alarm critically starts to blink and it stops. If we reduce the distance of sight, we can see the blind spot right and its advisory warnings, and the LED also blinking here. If we reduce the left side, we have the blind spot left and also the advisory buzzer beep. If we increase the motor, here is the mode is normal mode as the speed changes to above 40, the 50s range. If we now increase the motor temperature, it also stops the torque of the motor, the buzzer beep. Now motor is also restored in the normal condition. Now, first of all, let's go to the high speed overspeed here. And before that, we have seen the blind spot left, blind spot right, front, and also with the time to collision we can see here. And the speed, the speed goes above 100 kilometers per hour, it goes to the sport mode. Now let's one is reached the 120s bar. There is start to the advisory warning about high speed, and also the battery is decreasing rapidly. Now let's just apply the full brake, and the car goes in the regenerative mode. As we can see, the battery is going charging and the speed is decreasing rapidly. And here is the speed history graph. Also, if we ignore the warning and the speed goes on, once the battery dies, it also shows the car conditions as the speed is rapidly decreasing, battery charge. It goes advisory warning. And the load charge fault here, and the secondary relay initiates. Now, if we restart the board, it again goes in the starting conditions. Okay, that's for the simulation. Thank you.
We have seen the live simulation demo about how the STM32Cube help us to store code files and the Pixim Lab to simulate hardware working based on the code. Let it be the potentiometer or ultrasonic sensor or fault LEDs and also the Python dashboard working. Now, this project taught us a lot. We learned how to program hardware peripherals like GPIO, ADC, timers, and UART. We moved from simple relay-based code to interrupt-driven, multi-rate designs. We also learned signal processing, converting raw sensor reading into real values, and physics-based modeling, turning things like drag and heat loss into working code. We combined multiple sensors for collision detection and built a fault handling system using state machines. Finally, we designed our own serial communication protocol and built a real-time visualization tool to bring all the data to life. That brings us to the end. This is our capstone project on EV ADAS dashboard built with STM32 Bluepill, Pixin Lab, and Python as a part of our embedded internship of emertex. Thank you. Myself, Supradip Karmakar, a ECE BTech final year student from Jalpaiguri Government Engineering College.
Before wrapping up, I want to take a moment about how the project we came together because it's really a team effort. I am Animesh. I've covered the introduction to the foundational concept, the tool chain setups, ARM Cortex designs, architectures, and most of all the microcontroller STM32F103. From my teammate Debjit, I want to extend my special thanks and gratitude as he covered the architecture and simulation phase, the system, EV control module, the physics-based engine, SOCs, regenerative braking falls under his supervision. After that, I want to express my special thanks to Supradip Karmakar as it as he is the person who brought our project together in life. He built a Python and a Matplot dashboard that visualize our telemetry in real time, the speedometer, the SOC bar, and the ADS Buddies view. All together comes to the summary of everything we validated and learned the way. Individually, each and every pieces, the firmware foundations, the EV and ADAS engine, and the live dashboards, gives meaning to our project. Together, we completed a real-time pipelining and a real-time image capturing of our project. Overall, bringing together life into our laptop screen in hundreds of few milliseconds. We achieve our project EV, ADAS, and Dashboard Foundation. Altogether, I want to extend my special thanks to entire MRTech's eh, internship program. Beyond the technical internship and mentorship on the firmware and embedded system, they also guide us on the professional sides of things, helping us to structure our resume around the project and shaping how our LinkedIn works. A kind of guidance doesn't show up in the code, but it's just valuable where it goes to our action and our career decision. Thank you all for all their supports and hard work for our project completions. Thank you.